Okay, I'm just getting set up, guys. We're going to probably start in about 5 to 7 minutes officially. So if you're watching the recording of this, just skip 5 minutes and see if I've started. Otherwise, skip to 7 minutes. And I'll have started by then, whether anyone's here with me or not. Just going to give it a few minutes to see if anyone joins us today. And I want to test. Am I hearing myself in my microphone? Yes, I am. Okay. How's it going, man? Come on in. I'm just... yeah, we're going to look at Pythagoras Theorem stuff today. So that'll be, I think it's a couple questions worth of that assessment paper. For some reason, I'm hearing myself in my own ears. So if I start talking all funny, that's probably why. And I can't exactly figure out why. Was it echoing yesterday? Could be. Yeah, I've got exactly that, but it's right in my ears. I'm not exactly sure why, but I might be able to just mute this. Okay, now let's see, that's working. All right, so I guess we're about 5 minutes after 2, which is what I told people at the beginning to skip to, so we can pretty much get to getting, which will be sweet. So Pythagoras' theorem, you sort of know about this, I know, because you asked me about it yesterday. It is something that was come up with by a Greek dude who lived about 500 BC. And basically, he just showed that there was a relationship between the long side and the two shorter sides of any right triangle. Right triangle just means that they have this 90-degree. Need to calibrate the screen again. Never ends with technology. Sorry to anyone who's tuning in on the recording or online. I just need to make my pen actually know where I'm clicking. Because I walked away a few minutes ago and apparently undid all that. Yeah, so the recording yesterday when we were together actually didn't work. So I just now, like right before this, re-recorded a version where I was just talking to myself. So it's a bit fast-paced, but you'll be able to pause and stuff. And so we're just waiting for that because it goes to the cloud and then we can distribute it from there. So I'm waiting for that to go to the cloud and get sent to Delaire. And then Delaire will make sure that everyone has access to it, probably through that Facebook page. I'm not sure if you've seen. Okay, so perfect. So probably through that Facebook page, we'll send links to all the recordings. So tonight we'll end up with this one and the one for today, or yesterday, sorry. The one for yesterday will be kind of weird because you were there, but then it'll be like a weird version where I'm doing the same thing but without you. And it's just the whiteboard. You can't see me because I got confused and I didn't want to figure it out. Okay, yeah. Yeah, so something went wrong with the recording the other day. So hopefully today it's going to work. I think somewhere it says that it is in fact recording. Yeah, there's a little cloud right there. So hopefully that means we're recording and everything's working. Yeah, so Pythagoras' theorem just talks about right triangles. That's still not calibrated. We'll see how we do. Might have to do it again in a sec. It talks about right triangles and it relates to three sides. The longest side of any right triangle is the, no, okay, I need to recalibrate. Please work. This is the joys of doing classes that are like half online and half in person. Because if I was just using a normal whiteboard, we wouldn't have any issues. Yeah, there's not too many of us because it takes a certain amount of time to get through all the programs. So you kind of got to just like be in school your whole life. Like you can't ever take a break. Okay, so why? Do you see what I mean? How my pen doesn't match where it draws? Okay. No, and it wasn't doing that like 10 minutes ago. Sorry to everyone on the recording. What time is it? It's 2:08. Go to 2:10, 10 minutes into the recording, and hopefully I will have solved this. Why? I'm going to try again. I think we can actually edit the recording and cut a lot of this out. Hopefully. Maybe if I do it with my finger today? No, I don't want to do that at all. think we kind of have it. So Pythagoras' theorem relates the long side of a right triangle to the other two sides. Right triangle just means we have a right angle somewhere in it, 90 degrees. The longest side is always directly across from that 90-degree angle. When we label triangles to use Pythagoras' theorem, we talk about side A, side B, and side C. And side C must be the long side, must be directly across from the right angle. Side A and B don't matter. We get to pick. Let's do it like that, just because why not? Could have done BA, but C must be the longest side. That's the only, not the only, but honestly one of the biggest mistakes people make when they go through Pythagoras' theorem questions, mislabeling. So really take your time before you start these types of questions and make sure that everything is labeled as it should be, where C, the long side, is directly across. Pythagoras' theorem, as many of us have heard stated before, just states that A squared plus B squared equals C squared. This is a relationship between the squared values of the side lengths of each side of the triangle. And we can actually show this and like motivate ourselves that this is true. So to do that, I'm going to attempt to draw a picture. I'm not very artistic, so we'll see how it goes. But what we have to recall for this picture to make some sense to us is that the square of a value is, we call it the square because it represents the area of a square with that side length. Okay, so A squared, we could draw like this. And the area inside here is represented by the number that A squared would give you. Okay, similarly, B squared, and I'm going to draw this in kind of a weird place, and I'm hoping that it will make sense as we continue with the sort of proof. This is not something you'll be asked to reproduce. It's just something I think is interesting and kind of motivates that this works, because this is sort of an abstract formula you see and you're kind of like, oh yeah, sure, I guess that's true. But it's kind of nice sometimes to have just some inkling or have seen someone show you like, no, it does make sense. So if I draw B squared, we're going to arbitrarily decide that in this example, B is bigger. B squared. So, man, this is way off. So if this is B squared, then every side of this square is B, and every side of this square is A. I can fill in the rest, oh gosh. The rest of this to make a square, a bigger square, with side lengths A plus B and B plus A, which are the same thing. So this is a big square with area B plus A. And the last thing I can do is break these two rectangles I've added on into triangles. Okay? These triangles have side A, side B, and we're going to call this green side, side C. I can draw a similar square over here that is going to have the same side length, A plus B. So I've done B is blue. Oof. This calibration of the whiteboard is not ideal right now. So B is blue, and it's about that long. Could be. A is red, and about this long. And C is green, and we know by definition that C is the connection of those two triangles. So I said I was going to draw a square that was B plus A. So B is blue, that's the top side. The top side needs to add A. We already have B, right? So B plus A. Trying to be fancy with the colors because I think it is a helpful visual aid, but it is kind of annoying. That B is way longer, isn't it? Let's fix that. Now, if my drawing was very, very accurate, what we're ending up here is with a square of this. I've drawn B really long again. With the same dimensions as this square and the same 4 triangles that this square has in it. Okay, that triangle is the same as that triangle. This one all of these triangles are identical. They all have side length ABC, right? And if we finish this drawing, we're going to notice some amount of area left in the picture. So if I connect those, this triangle here matches to that triangle there, or any other triangle. They're all identical. This triangle here can cancel that one. So the way I'm thinking about this is canceling area, right? These two pictures are squares of B plus A, so their area is the same in total. Okay, so yeah, right? So all these triangles are exactly the same area. But in this picture, we have area A squared and area B squared. And in this picture, what do we have? Area C squared. Right? So if these squares are the same area, which I hope we can agree, because we have side length A plus B on all sides, unless I've drawn something wrong, then, and if these triangles are the same size, which again, I think we can convince ourselves by looking at the diagrams and just thinking for a few moments, that this is a triangle with side length ABC, ABC, and similarly there, and those four, then the areas left have to be equal, right? And the areas left just so happen to agree with Pythagoras' theorem. We have A squared and B squared exactly the same as C squared. So again, not something you'll ever be asked to reproduce, or would ever have any reason to reproduce. Just an interesting way of seeing it, right? It's nice sometimes when we work with these types of math to see them and get why that happens, and convince ourselves. So then when we're using it, we can use it a little more, oh, it's supposed to do that here. Look at that. We can show Pythagoras geometrically as follows. I did that above. Yeah, exactly. Not paying attention to my own planning, but that's okay. So let's do an example. Use Pythagoras. Also, sorry to anyone online for the noise. They're building a deck. Nothing I can do. So we can use Pythagoras' theorem to solve various triangles as long as we have two sides. So let's do this example here. We have, oh, can't pick up the pen and move the screen. We're looking for x. We want to use the formula a squared plus b squared equal c squared. And we have to be careful about our labeling. So the right angle is right here. Directly across from the right angle is x, which we are going to call c for the use with Pythagoras' theorem. Oh God, it's getting loud. I really hope that everyone can hear me. I'm going to try to talk loud enough that the microphone can hear me okay. Once we've labeled C, that's directly across from the right angle, A and B don't matter. Let's just decide. Let's call 5 equal to A and 12 equal to B. So we have all three of our sides labeled. Now all we have to do is use our formula, okay? A squared, A is equal to 5, that's 5 squared. B squared, B is equal to 12, that's 12 squared. C squared, we don't know. That's what we're looking for. So we just leave it. C squared, okay? We are going to solve this equation. To do that, we start with the numbers we have, 5 squared and 12 squared. Let's evaluate those. And I'm lazy today, so I'm going to use a calculator. Clear whatever is there. And 5 squared is the same as 5 times 5. That's 25. So 25 plus 12 squared. Clear that. 12 by 12. 144. So 25 plus 144 is equal to what? C squared. Right? We still don't know what C is, but we can just carry it along with us. I'm just going to pop this back up here because I'm running out of space on the bottom of the board, and still hoping people online can hear me. So if we evaluate 25 and 144, 169, yes, that's right. See, you're good at math. That is equal to C squared. So Square root of 169, I think is actually a nice square root, but let's do it in our calculator. So if we go square root function of okay. So every calculator is different. This calculator wants you to type the number and then square root that. So this is a 169, and then this button right here is the square root button. It gives us 13. We can double check and make sure we did that right. Oh, why do I keep hitting that? Oh, it's because my board's not calibrated. 13 by 13, 169. So remember, when you square root a square, square roots and squares just cancel. They're the opposite of each other. It's like division and multiplication. So we can get rid of that. That's C. And because I square rooted this side, I have to square root that side. Right. So it's that's the trick to remember, is really that square roots cancel squares. Okay. So we make sure we do the same thing to the left side of the equal sign as the right side, and make sure we remember just how do square roots operate and how do they change algebraic representations, right? It's very easy for us when we have numbers to go through and figure out how things change, because we just type it in the calculator and it tells us, right? It's a little more difficult when we have to work with this sort of symbolic representation. And that's where this remembering things like square roots and squares are inverses, so they get rid of each other. They nuke each other. So we'll get rid of all this. And I really apologize to anyone catching the recording or watching online that it is so loud in here right now. I really hope you can hear me okay. If there was anyone live, I would get them to tell me, but I don't think there's anyone live. Okay, so another example, very slightly different. All that's really changed, though, is the triangle has moved orientation, right? So it's labeling. This is a labeling trick. Which side is C across from the right angle? Right? Straight across from the right angle has to be C. Everything else doesn't matter. Let's call this A, and let's call this B. Right? So remember, labeling is not the hardest part, but the most common mistake. So take a few moments, double check, make sure your labeling makes sense. And then we go straight from the top. We go A squared plus B squared equals C squared. I always write this, even though I know it, I write it at the top of every Pythagoras problem, just because it reminds me, it organizes me to start my math, right? So A is equal to 8. 8 squared plus B, we don't know it, but it's called Y. So let's just put in Y there. Y squared, and all of this is equal to C, which is equal to 12, right? C squared, I should say. So 12 squared. What do we do? Start evaluating, right? What do we know? 8 squared, 64. I'll help you with that one. So 64 plus Y squared, we still don't know what it is. Just leave it there. Well, 64 plus Y squared is equal to 144, right? Right. Do the same thing to both sides of the equals sign. We can take away 64 from both. We're going to get that Y squared is equal to 80. Is that right? Let's check, right? Did some math, not exactly sure. 144, take away, not divide. 144, take away 64 equals 80. Excellent. So that leaves us with Y squared equals 80. We want to figure out what Y is. Square root both sides. You can do the same thing to both sides of any equation, and it's totally allowed. Square root and the square cancel. Then we get Y is equal to the square root of 80, which is equal to 8.94 some other stuff, right? I don't want to write all that, so what I'm going to write is just 8.9. nearest rounding to a tenth. It's pretty reasonable in almost all cases. So 8.9. You could round it to 9 if you wanted, yeah. Doesn't really matter. The rounding is going to be determined depending on the application, right? So if this is a piece of a roof, if this is a beam for a roof I'm building, I'm going to want to do the 8.9. I'm going to want to get as close to right as possible. Otherwise, my board that I get to fit on top of the roof ain't going to fit. It's going to be off by an inch at the top and you're going to leak. So, right? So it all depends. If this is my house of cards, it doesn't matter, right? 9 is just as good as 8.9 for a house of cards, right? So your rounding is always going to depend on application. My rule of thumb when I'm doing a math test or class, I just round to 1 decimal point. It shows that I know it was rounded and that it did have more values past whatever the whole number is, but it's not too much work. So that example you noticed, right? We solved for something other than C, so we had to rearrange the equation a little bit. What did we do next? Let's see. Okay, one more here, and then we're on to word problems, the bane of everybody's existence. So, what do we do first? We figure out what side is C, straight across from the right angle, right? C equals 15. A and B don't matter. I'm just going to go left to right. A equals something, and B equals 12 centimeters. Now remember yesterday we talked about units. We're lucky here. The units are both centimeters, so we don't have to worry about them. They match. If those did not match, we would have to convert one of them so that they did. Okay? Otherwise, our answer makes no sense. We start multiplying meters by centimeters, and it gets kind of confused, right? It's like multiplying a table by a chair. It doesn't work. So, yeah, tables and chairs is my favorite example. I think I did it in the re-recorded version as well. So we start right from the top with our formula from Pythagoras. A squared plus B squared equals C squared, right? A squared, we don't know it. Let's just leave it as A squared. Plus B squared is 12 centimeters squared. And that is equal to 15 squared. Okay, A squared, we still don't know it. Plus 144 is 12 squared. All of this is equal to, I think 225, but I don't know. So 15 times 15. Hey, look at that. 225 is 15 squared. Okay. We can do the same thing to both sides of the equation, and we want to isolate our variable, A. So what do we have to get rid of? We have to get rid of the 144, because it's right sitting next to the A, and we don't like that. The A wants to be on its own, just on one side of the equals sign. So we subtract 144. We subtract 144. We're going to get A squared equals 225 minus 144. I don't feel like doing that in my head, do you? No? Okay. 225 subtract 144, 81. So that's great. We've got A squared equals, what did I do? Saved it. A squared equals 81. That's totally fine. So we want to keep going. I'm going to bring this up here just because I'm tall and that's getting low down. So how do I keep going from this point where A squared equals 81? Well, I square root, right? Get rid of the square. So squared and the square root go away. We're left with A is equal to square root of 81. Do you know that one? 9. You got it. Yeah. No, you said it. I heard it. Right? A equals 9. 9 what? Centimeters, right? We started with numbers in centimeters. We're going to end with numbers in centimeters. Units are important. Again, if this was a roof and someone said, ah, shit, how high does this roof need to be? Right? And you came back to them and you just said, ah, it needs to be 9. They don't know. They don't know what you're talking about. 9 centimeters in this example. It's a pretty small roof, I admit, but. Right, so it starts to make sense when the first time you ever have someone give you an answer to your question without units is when you start to realize just how important the damn units are, okay? So moving on, we can also solve problems that are not obviously triangles or Pythagoras theorem problems with Pythagoras theorem. I'm just going to wait a minute. Okay. So in this case, we have a ladder that's being placed on the ground in such a way that it reaches the top of a 12-meter high wall. We want to find the distance of the foot of the ladder from the bottom of the wall. So when I do word problems, my first step is always, always, always to draw a picture. No matter how bad it is and how embarrassing it is if everyone sees it. We have a wall, okay? That's a wall in my math drawings. And it is 12 meters high. Oh. It's 12 meters high, okay? So I'm going to label that here. And we are placing a ladder that's 13 meters long. And it's going to touch the top of the wall. So my ladder is going to go something like this, and it is 13 meters long, okay? What else do we have? Find the distance from the foot of the ladder to the bottom of the wall. This distance here. The foot of the ladder to the bottom of the wall. Okay. Yeah, so it's one of these, again, it's that parsing, right? Once you get it to here, this picture, now it's the same question as above, right? Now it's something we've seen before. But when it's written like this, it takes that whole step of translating the English to math, right? Which is a really weird thing to get your head around, but once you get really good at it, and it's just taking your time. Yeah, so it's a really careful process, right? For me, it's, okay, draw one thing at a time and find every clue in the question about that thing I can. So right here, I drew the wall, and I said, what do I know about the wall? Okay, I said, what do I know about the wall after I drew it, right? And I figured out, I know it's 12 meters high. Okay, well, what else do I know? There's also a ladder. Draw the ladder next. If you have them available, colors help a lot, right? You'll notice I switch pens a lot. I think it's really useful. It helps you sort of tell the difference between things. But in any case, once we get to this point, we just have to figure out how we're labeling this. Right? That's the right angle. If it's a vertical wall off the ground, you're going to have 90 degrees at the bottom of the wall. So in this triangle, that's the right angle. That has to be C. Okay? C is equal to 13 meters, and A squared plus B squared equals C squared. Let's call A the blue side and B the green side. Okay? Hopefully no one's colorblind. Please email me and tell me if you are. I will stop using colors as reference. A squared is 12 squared plus B squared. We don't know. We'll just leave it as B squared. That is equal to C squared which we've said is 13. Square that. All right, now we're doing stuff we know. 12 squared, 144, plus b squared, we don't know it. Oh, this is really needing to be calibrated. I'm going to do that in a sec. 13 squared, 169. You said it. Okay, so 13 squared, 169. So 144, we can take it away. We want b on its own, right? Subtract 144. Do the same thing to the other side of the equation. Can't do it just to 1. It'll get jealous. That's what happens, right? 144 minus 144 is 0. So all that's left on this side is b squared. And this is equal to 169 minus 144, which I'm going to use a calculator for. If I can get my board to work. What did you say it was? 25. 169 minus 144. Ladies and gentlemen, we have a genius in the audience today, in the flesh. 25, right? We're lucky. Why are we lucky? That's a nice one. Square root, that cancels, just like always. B is equal to 5. We're lucky because it's a whole number. Right? It's one of the ones, it's one of the squares we know, we've seen before. We might not remember it, but we know it. Okay? So there's one word problem, one example. Hardest part is the diagram. All of this mess is what we did above. Also, I'm going to calibrate my board now because this is truly a mess. So I'm going to erase this and do that before we go to the next question. Come on, there we go. That's pretty cool. Oh, I wonder if it thinks I'm using my right hand. Because I know this board asks you what hand you write with. So maybe that's why it's not working. Anywho's it's. Well, let's see. Oh, so much better. All right, we're in business, guys. Test. Okay. The height of two buildings, that's typo. That should have an S because there's two of them. Plural. The height of two buildings is 34 meters and 29 meters respectively. So, okay, I've got one building and I've got two buildings. Okay? If the distance between the two buildings is 12 meters, okay, so that's something I know, right? The distance between the two buildings is 12 meters. Right? Find the distance between their tops. Okay. First thing I'm going to say is that maybe I should have drawn these more drastically different in height. Right? Just, now, this is pretty accurate. 34 and 29 are pretty similar numbers. That's the heights. But for our drawing, it's going to look better if they're more drastically different in height. This will exaggerate any triangles we can exploit. Okay. So this is the shorter one. So the shorter one should be 29 meters tall. So that's 29 meters. The taller one, the red one, is 34 meters tall. So this is 34 meters tall. We want the distance between their tops. Here to there. Okay, it's a weird distance to need, but that's the one we want. So how can we make a right triangle? If we go straight across, right? right? So holy shit, now we got a right triangle. That's pretty sweet. What are the sides of this triangle, right? Because this is 34 meters from the bottom to the top. But we don't need all this bit down here, right? But this bit down here has to be exactly the same as this bit over here, the height of this building, because we drew straight across, right? We drew straight across from the top of this building to whatever point that we wanted on the other, okay? So this distance right in here has to be the height of the taller building. Take away the height of the bottom building. 5. Right? Now we have, I can like take this black triangle I've drawn here, I can pull it out of the drawing. Okay? That's the same triangle here and here. One has a bunch of diagrams and pictures all around it. One is just a triangle like we're used to. We said the height was 5, and we know the distance between the buildings is 12. That's that side. Okay? What side is C? Directly across from the right angle is C, and A and B don't matter. So let's say A equals 12, B equals 5. Okay? Pythagoras tells us that A squared plus B squared equals C squared for any right triangle. For this right triangle, A equals 5, that's 5 squared. B, I totally read that wrong. A is 12, not 5. So A equals 12, 12 squared plus B equals 5, that's 5 squared. All of this is equal to C squared, the value we want to find, right? This line in my triangle I pulled out exactly represents this line in the diagram I drew, okay? 12 squared is 144, plus 5 squared is 25. All that equals C squared. 144 plus 25 is 169. I think this is a number we've seen a couple times today. Square root of both sides. Square root cancels the square. C is equal to 13. Okay, we can check if you don't believe me, because I did do that in my head, right? 13 by 13, 169. So the square root going the other way gives us 13. So again, once we've done the picture, this is the same as before. It's relatively speaking easy compared to the picture, right? Taking the English and making it into math is by far the hardest part, right? So we're going to keep doing word problems throughout the rest of the units that we do and get more and more practice parsing through them and understanding what they mean. I think that's all we have planned for today. Feel good? Yeah? Excellent. Hopefully you guys feel good. I'll make sure I can print you the worksheet questions associated with today if you like. Everyone online, they should be available on the Facebook page along with this recording. Thanks for watching. Again, so sorry for the noise. I wish that was something that we could have dealt with better, but that's just how it was today. I'm going to end this meeting.